students, welcome back to Chemical Kinetics. Here on, in the next few modules, we will study about first order reactions, starting with this module. Now here, we are going to understand the general rate law and the differential rate equation for first order reactions. So let's get started. Once again, let me reiterate the term first order reaction, meaning that suppose if there is a reaction, reactant are giving products. For this reaction, order is 1. Now let us say Cr is the concentration of the reactants. So if we have to write the general rate law, that is the rate law expression, for this reaction we can say rate, that is R, is directly proportional to concentration of the reactant raised to N, where N is order of the reaction. Now this expression can be also written as R is equal to K, that is rate constant, into concentration of the reactant raised to N. We already know what is rate constant, and we know this representation of the rate law expression. But here in this case, it's a first order reaction, meaning that N is equal to 1. So substitute this value of N in the rate law expression and you will get R is equal to K into concentration of the reactant. Now, if you try and understand what this expression really is, you will see that as concentration of the reactant changes, rate of the reaction will also change. Which means if Cr changes, then R will also change. This means that Cr and R are the variables in this equation. Also, this equation resembles y is equal to mx plus c, that is equation of a straight line. Here y is similar to r, m, which is the slope, it is similar to k, and x is similar to cr. Yes, of course, c is constant. So this is the equation of a straight line passing through the origin. Upward slope because k is positive. So let's plot this graph of rate, that is R, versus Cr, concentration of reactants, y versus x. Now this, as I told you, will be a straight line passing through the origin, and when you find the slope is nothing but k. So that's how you represent the general rate equation graphically. Also, with the help of this general rate law, R is equal to K into Cr, we can also get something which is known as differential rate equation. It's really very simple, guys. All you have to do is take the same reaction, reactant giving product. And for this reaction, again, we have to consider Cr as the concentration of the reactants. Once again, we have to apply the general rate law. We have to write the rate law expression for this reaction. So we will get R is directly proportional to concentration of the reactant raised to N. Once again, we have to consider that it is a first order reaction, so N is equal to 1. So all we have to do is substitute all these things in the rate law expression. We will finally wind up with R, that is rate of the reaction, is equal to K into Cr raised to 1. Now we have already seen this. R is equal to K into Cr. But I also want you to remember the definition of rate of reaction. Rate of reaction is nothing but change in the concentration of reactant or product per unit time. So we can also write rate of the reaction as minus dCr upon dt, that is change in concentration of the reactant with change in time. Negative sign indicating that it is a reactant, it is decreasing with time. Now if you take a look at these last two equations, the left hand side is the same. So I kind of have a situation here where A is equal to B and A is equal to C. So naturally B is equal to C. So I can write, by comparing these two equations, I can say that minus dCr by dt is equal to kCr. And this, my friends, is called as the differential rate equation for first order reaction. kCr comes from the rate law expression and minus dCr by dt comes from the definition of the rate of reaction. So this is how you derive the differential rate equation from the general rate law. That's all for this module. We will study some more things about the first order reaction in the next module. But till then, take care.